Sumatera Utara and also from Petra Christian University. So we'll learn about IFN, this ideal flow network for recommendation system. So recommendation system or market basket analysis is information filtering system that provides suggestion for the items that are most pertinent to particular. So our goal is actually to automate the decision making process by providing personal and highly quality recommendation. This is example in Amazon. For example, you can see books. Okay, for example, if you buy to find the business intelligence, then Amazon will create research, or a person who buy this item also buy something else. Right. So MBA or a market basket analysis is a tool of knowledge discovery about co-occurrence of nominal or categorical items. So it's a data mining technique to derive association between two data sets. Our data are categorical, both and out. And the output of this analysis is creating association rule. This new knowledge directly from the data. Now, usually the association rule is in the form of X. If X, then Y. So in this case, you can see the left-hand side is the antecedents and the right-hand side is the consequence. So that means if people who bought this item on the set X are often bought items on the set Y. So the X can be item sets. So for example, bread and cheese, and then the Y can be other item sets as butter, jams, milk, and honey. So the usual way to do this MBA or market basket analysis is to define what is called support and confidence index. Okay? With support is basically the intersection between the two sets of left-hand side and the right-hand side of the equation. Okay, so in this case, we find the number of intersection data, and confidence is practically the conditional probability to obtain the set Y given the set X. So, right now the exhaustive approach or the naive approach is to generate all possible association rules. Okay? And then for each association rule, we compute the support and confidence, and then we apply two thresholds, which is the minimum support and minimum confidence to obtain the association rule. However, this approach will go to combinatoric problem. Okay? So say with only 500 number of items, you get a very large number of total possible association rules. So it's very difficult to generate manually. So there is already exists what is called a priori algorithm to prune these possibilities. And our approach is to use an alternative approach that we call as ideal flow network. So the a priori algorithm is basically pruning all these item sets here. So based on the assumption that if there is any item set which is infrequent, that means we cut based on the threshold, then its superset should not be generated. So if the item set is not large, so then we can cut all of these points below. Right, so our proposed idea is to use what is called ideal flow network, okay, which is practically the most natural technique to create the product graph for the recommendation system. So the nodes here represent the items, while the links will represent the co-occurrence relationship between items. So I would like to discuss what is ideal flow network. Okay? So what is IFN or ideal flow network? It's a steady state relative flow distribution in a strongly connected network where the flow are conserved. So basically, in short, IFN is irreducible premagic. Irreducible means a strongly connected network, and premagic means the flow, total flow in equal to the total flow out. Okay? So, idea of IFN start from a random walk on a random network. So, given a random strongly connected network, at each node we can select any available links, okay, with certain probability distribution that we know, okay, and then we do random walk and we record the link flow, which is the sum of trajectories, and this agent will keep moving until the time is infinity. Okay? So, and this is an example. So we have a very simple network with only 5 nodes here. Okay, so if we create, say, 200 agents with, say, 1,000 time steps, okay, the number of flow will increase something like this, because it's random, so we will get different values. But the nice thing about this is, once you divide, okay, the flow here, okay, the positive flow here with the minimum flow, so this case, the minimum flow is like 150. Okay, so and we run it up to infinity. These numbers will automatically become the asymptotic value, okay, with this integer. So this integer is with this we call as ideal flow network. And the nice thing about this ideal flow network is you see the sum of the columns here, the sum of the columns and the sum of the row are exactly the same. So this properties that the sum of rows equal to the sum of column represent, we call this premagic. Okay? That represent the conservation of flow in each node. That means the total flow in is equal to the total flow out. Right. So regardless the number of agent and the simulation time, okay, when this multiplication is quite large to fill the network, we will have a asymptotic value. Okay, this limit will always create integer. Okay. So this is what is called IFN. So basically, irreducible or strongly connected network. So when we say strongly connected network means from any node you can go to any other node and you can go home. Okay. So, and second term characteristic is premagic or for preservation. That means the total inflow is equal to the total outflow in each node. Okay. So in this example, very simple network here. So if you have start from node here, so say this is the flow here is Y and the flow there is Z, then of course the flow in must be Y plus C. The same thing here. If this link here is X, then you will get flow in is equal to flow out, then this must be X plus Y plus C. And this is relative flow. That means positive scaling will produce equivalent network that preserve the stochastic probabilities. So we also assume that the network is fully utilized. That means all link flow are positive. Okay. So why we use IFN? Because again, the code are available for free in GitHub. Okay. Also, you can also use Excel plugins that's also available in Revoledo. Also, there is also online version. It is used on HTML and JavaScript. So why we use IFN? The IFN itself originally come from a traffic flow network. Okay, so then we will use a traffic flow network as a modeling metaphor and name convention. For example, the flow itself. Yeah? The flow is represent the wave. Right. So it can be applied to any model, any problems. Okay? That as long as we have the problem at hand can be translated into a strongly connected network and the flow. So IFN itself has been applied for transportation and also for supervised learning and so on. So our attempt here is it possible to use IFN for data association or recommendation system. So let's come back to the IFN for data association. So in this case, its node represent the items, okay, and the link represent the relationship or go together. So this relationship is bidirectional, mean that one item purchased together with other item. That means one win and the others are the same thing. So in this case, the matrix is symmetric. So the technique is just scan the data that goes together as additional count in the adjacency matrix, okay? And then we can compute the IFN. So the association rule here is simply getting the link flow, okay, that above certain threshold. So to compute IFN, we need to compute this kind of matrix, okay? But we found a theorem that we can avoid this kind of computation to make the computation faster. Yeah? So if we can create trajectories of the items set, okay, as cycles. So suppose we have a set of cycles C here, capital C here. So then we can define what is called flow set. So this small c here is an element of the set of cycles. Okay, so you can see here this is a cycle. So the begin with the first node Vi and the end with Vi again. And say we have I and J is a link. Then we put that into the flow set. Now the count of the flow set will be matrix. So our theorem said that, look, if you have cycles and put that into flow set and flow matrix, then the flow matrix will be exactly parametric and irreducible. So this is exactly the ideal flow matrix. This will fasten the computation along. Okay, so I try to create the algorithm to do this. So to create that algorithm, we need a set of operation. Here we define what is called overlay operation. Okay? So this is the symbol of overlay operation. So say we have a network FA, okay, and we have another network FS. Okay? So this FS is a system, A is the actual network that you get from the data. Okay? Then we can overlay the network that we get from the data into the system, okay? Iteratively. So this is the definition of overlay operation. So for each edge of node 1 and node 2 in FA data, okay, with the certain flow, so check whether that link exists or not exists. Yeah? So if does not exist, then we create that flow. If it already exists, we simply update the flow. Okay, so this is an example of overlay operation. So say we have ABC and we have this the system network. Okay, and you see here we have already 3 with AB. So then when you overlay, then we just add into additional flow. Now the same thing with BC. Okay. BC is already 5, then we add with 1. Okay. And CA does not exist, right? Then you can add here as a new link. So this is the meaning of overlay operation. So if the link does not exist, you create, but if there is already exists, you just update the flow. Okay. So then the algorithm of IFN association is very simple. Okay. So for each item set, okay, that we get, so this is an online or algorithm. That means for every transaction that we get, we create a simple complete graph. Okay. And then we just overlay that complete graph into the system. Okay. And to predict the association from new data, say for example, transaction list of the item, it's called this L. Okay. So we set the prediction as empty. Then for each item in this item set that L, okay, then we can check, okay, if N is within this Fs or not. So if this is within the Fs, then we get the adjacency node with this N2 in the Fn, which is not in L. Okay, and then we update the prediction set here, and then finally we can return the prediction. So once the difference with the a priori algorithm is in a priori you compute the index of support and confidence. Okay, using IFN is the other way around. So this algorithm is much faster because we don't actually do the combinatoric of all the data set. So again, the definition of support and confidence are exactly the same as in the a priori algorithm, but we use it in terms of the flow. So again, for getting the prediction, okay, the result of the prediction will be association rule, which is the flow between one node to the others. Okay, and of course that node will be based on what is the current user have. Okay. Okay, so to make it understandable, so I give you example. So I have only 7 item sets here. So it's 7 transaction data. It is only 4 items: apple, banana, cherry, and durians. Okay, and we want to create a recommendation system based on IFN. Okay, then the question is to predict, okay, what is the system should suggest if the new customer actually buy cherry. So because the order of the items does not matter, so we can use our theorem a while ago. Okay. We have only 4 items in this example, so clearly we have only 4 nodes because 1 item is equal to 1 node. Okay. And then from the trajectory data, we create a link permutation, okay, of the unordered data. So the link permutation is basically the same as a complete graph. Okay. Now, based on the trajectory reading, you can create a network structure and the capacity matrix, and finally compute the stochastic matrix. So here is the example. So initially we have only, this is the 4 items, empty network. Okay. And then our first transaction is, say, A, B, C, D. Okay. From here, we can create a link permutation. That means from A related to B and B related to A. Yeah. So A to B, A to C, A to D, B to C, B to D, and C to D. Right? And the other way around. So in this case, we can fill up this matrix, and we can see this is kind of adjacency matrix that we can put it as a network. So this is a complete graph. Right. Now, this complete graph becomes the system for the next data. So we have the second transaction data, say only AD. So AD, we create a complete graph. Okay. And we overlay with the system a while ago to create a new system. Right. And the same thing, say this is the third data. Okay. Again, we overlay and we create a new system. Yeah? This is the new data set with this complete graph. We combine, we overlay with the existing system to create a new system, and so on. Right? So this is the 4 data. We have on DBC. So this is the complete graph, and this is the earlier system. We overlay, we create a new system, and so on. Okay. So our final data, we get this kind of capacity matrix, which is already irreducible and symmetric. So and the IFN theory states that the capacity matrix surely will be irreducible and pragmatic. Okay. So then we get already the ideal flow network. Right. So this is the network that we have. From here, we can do a prediction. Say for a new customer who bought cherry, the system would recommend this one. We get durian, because among all the items, the third row earlier, so the third row here will produce the highest flow. From cherry to durian is the highest. So this is the percentage of matching. And not only that, we can also rank the fruit. In this example, based on the popularity, simply by computing the sum of row or sum of columns. So in this example, we know the highest is 10 out of 32. So in this case, durian is rank 1, and rank 2 is 8 out of 32, so 25%. And the three of them, the apple and cherry is both are 7 out of 32, represent the popularity in here. And the nice thing about IFN is, look, this number represent the relative strength. So in this case, we can say that, so banana in this case is 1.14, with this 8 over 10, 8 over 7, more often bought than up. So based on this, so if you have another customer bought banana and cherry, what would be the recommendation system? Then of course we can put into the program and we can get the actual recommendation with this durian. So right, so with this we have extended the ideal flow network into an application that can be used for recommendation system. Okay? That can do online prediction, do rank popularity, and obtain the relative strength. Okay? Right. So actually, we have also I also apply this into INCA dataset from the French consumption table. So this is the consumption table in INCA dataset, which is open data. And we apply this about 500,000 record. Okay? So this is the data, which is originally in French and recorded into English using Google. And so this is the person ID and the ID of the items, and we can get this basic analysis of the data. Okay, and this is the usual crosstab, right? And from here we can do the IFN analysis, so we can train that. Okay, so we can train the IFN. And out of, say, 70 million flow, okay, you can see the training is only about 4 minutes. Okay? And to predict, it's just micron. Right, with this, I would like to stop my presentation. If you have any questions, thank you very much.
Okay, thank you very much. And now we still have 10 minutes. I'm sorry for Professor Novas that we don't have any question answer. Maybe we can do this together. To combine the two presentation. If anyone want to have a question, please. Thank you.
Thank you. So excuse me, I have a question for the second speaker, Professor Paulo. So in your research, I think this is a very good, very interesting talk. So First, I would like to ask about whether you, prior to train the model, whether you do or perform the feature selection first, or another pre-processing step, for example, like outlier removal from the data, because as I see, there are many features on your case study. I think this is a question.